Good morning and thanks for the kind invitation. Just a few words to present myself. I work at Holland Innovative in the Netherlands as a reliability specialist. Holland Innovative is a company that provides consulting services specialized in reliability and product and process development. Before moving to the Netherlands, I worked as a researcher at EPFL PV Photovoltaics and Thin Film Electronics Laboratory, where I was involved in the study that I'm going to present today about 35 years old PV plant. This study was done by EPFL and SUPSI, the University of Applied Sciences and Arts of Southern Switzerland, in collaboration with JRC. So the TISO 10 kilowatt solar plant is a PV plant installed on the roof of one of the buildings at SUPSI in Lugano, Switzerland, where the climate is temperate. What makes this installation unique is the fact that it's the first grid-connected PV plant in Europe. It was connected to the grid in 1982. Moreover, the history of the plant is very well documented throughout the 35 years of its operation. I'm gonna first talk about the modules and their power degradation over the years. Then I will briefly talk about degradation modes, but will focus in particular on the encapsulant yellowing. And finally, a short discussion on what can we learn from such an old PV technology and what are the lessons that are transferable to PV industry of today. These results are subject of two papers that we published in Progress of Photovoltaics. We have part one, where we talk about the electrical characterization of the modules. And then in part two, we cover the physical degradation modes and the discussion about PV technology. So the solar modules were manufactured by Arco Solar back in 1981. They are made of 35 cells, monocrystalline silicon, with a thickness of around 330 microns. The interconnections, as you see here, are made of only two ribbons, and the encapsulant is PVB. They are glass backsheet modules, but the peculiarity is that the backsheet contains a steel foil, which actually makes it impermeable. Plus, we also have an edge sealant, and also the junction box itself is very tight, as you see here, it's closed on all sides. All these make the construction of the Arco solar modules having a very solid sealing. There are 288 modules in the installation. Out of these, 18 were selected and were characterized regularly over the years. We call them reference modules. This is a bit the history of the measuring system that were used to obtain the IV curves. This is well described in part one of our paper. So the results are here. This is the Pmax variation of these 18 reference modules, normalized values. And here from the box plot, we see that the power distribution at the beginning was very narrow, but then over the years it broadens, so indicating that not all modules degrade to the same extent. Here the same values, but let's focus on the thick red line, which represents the average value. We can see that over the 35 years, the degradation was not linear. We can see that degradation rates increased over time. So in particular, the wear out phase of PV modules is characterized by nonlinear behavior. Now about the full set of 288 modules. Here we have the distribution of the maximum power of all the modules in different years. So this one is for the initial in 1982. And we see the power distribution is described by a Gaussian distribution with a mean value of 35.56 watts. This is the value that we use as initial value to calculate the degradation rates. So we don't use the nameplate value. After 19 years, in 2001, the 288 modules were measured, and we can observe that we start to distinguish two groups having different degradation rates. In 2010, so after 28 years, the degradation rates continue to increase. And finally, the situation at now, let's say 35 years, where we clearly distinguish two groups. The first one having a remarkably low degradation rate of 0.2% per year. But now this group is only constituted by 21% of the total population. Instead, the majority of the modules, 73%, they are described by a negatively skewed distribution with an average, with a mean degradation rate of 0.54% per year. So now it's interesting to ask what happened in these last 7 years. So here we plotted the degradation of the maximum power against the variation of ISC, VOC, and fill factor for year 28 and below for year 35. What we see in the situation of year 28 is that the Pmax losses are clearly correlated to fill factor losses. Instead, at year 35, we see a shift down of the ISC values and a corresponding shift to the left of the fill factor values. We can clearly distinguish the two groups that we identified before. Group 1 with a little power degradation of maximum around 10%. These modules are, we can see here, characterized by moderate losses in fill factor and ISC. Group 2, the one with the stronger power losses, is interesting now because we see again, as in year 28, strong power losses are mainly related to fill factor losses. But this region here, let's say between -10 and -20% of Pmax variation, this power loss is mainly attributed to ISC degradation. So what are the degradation modes that are behind this degradation? At the 35 years characterization, we employed different methods. So we did IV curves, electroluminescence, infrared, and a detailed visual inspection. We identified several degradation modes, and you can find a description in part 2 of our paper. Here, just to give you a glimpse, this module is a particularly degraded one. It presents at the same time encapsulant browning, front delamination, burn marks, and interconnection discoloration, and hotspots. So here you see the effects on the IV curve. This is the initial, and after 35 years you see the effects of the various degradation modes. So in general, we tried to relate power losses to specific degradation modes, but this was not always possible due to such cases. A degradation mode that is particularly interesting in this PV installation is the encapsulant yellowing. Not all modules experienced the same extent of encapsulant yellowing. In some, the encapsulant is still transparent. In others, we have a mild yellowing and often localized on the central line of cells. And other modules are completely brown. This is the figure at 35 years that we showed earlier. We just split the plot in two. Here we plot class A and C, and below class B, just to avoid overlapping. Okay, what we observe is that all modules of class A are in this region here, so with a very limited power loss. And also it's interesting to see that they didn't only experience strong losses in ISC, as we could expect, but also in fill factor, so meaning that the interconnections and in general the diode properties of these modules are still very good. If you recall the distribution of the power at 35 years, we had the two groups. Group 1 of modules with a very limited power degradation, and group 2 that was described by the negatively skewed power distribution. So we can conclude that all modules in class A, they all belong to group 1. Modules of class C, which are the full points, they experienced stronger power loss, as we could expect, and it's in some cases due to losses in ISC alone, and in some cases combination of ISC and fill factor. Finally, modules in class B, they show a more varied behavior. So we try to understand the reason for this different extent of encapsulant yellowing, and a former Arco Solar employee, he confirmed that at the time these modules were laminated with PVB, and that Arco Solar was using 3 suppliers, which were using 3 different formulations of PVB. And so to summarize, we have 3 different formulations of PVB corresponding to the 3 classes of the discoloration. And of these, we have 2 formulations which correspond to class A and class B, which show a remarkably low degradation rate. In particular, modules of class A, they are still performing at 95.1% of their initial power after 35 years, which is really an excellent performance. Here again, we remind the relation with the power distributions that were measured at 35 years, and we have that all modules of class A, they belong to group 1, so this here with very limited power losses, while group 2 is made by almost all modules of class C and around half modules of class B. And finally, we come to the last section. What do we learn from such an old PV technology? Of course, since 1981, when these modules were manufactured, there was a tremendous progress in the PV industry, in particular, actually due to the cost reduction dynamics. So we have that the Arco Solar modules, they presented some drawbacks, but actually their design offers also some advantages with respect to the modules of today. Here we have projection for the use of different module structures, glass and glass foil. And even if for the moment glass backsheet is widely the most used encapsulation scheme, we see that glass is gaining market share in these years and in the next years. We remind that the Arco Solar modules considered in this work, they are glass backsheet, but actually the backsheet is impermeable, and therefore they are closer to a glass structure rather than a glass backsheet. So that the lessons learned in this study, we believe that they are more easily transferable to glass modules. These are instead the figures for the encapsulant. We see that EVA is by far the most deployed encapsulant for PV modules, and is going to be also in the next years. However, if we talk about glass modules, it's well known that EVA has a problem of acetic acid generation, and therefore we need alternatives such as PO or PVB that was considered in this study. What we have learned from our results is that if we were able to recreate the same formulation of class A modules, then we would be able to manufacture modules with a lifetime longer than 35 years. The PVB has some drawbacks, but it also has some advantages. For example, it has already developed synergies with other industries, and this would give advantage in the manufacturing. So all these factors might open up some doors to the deployment of PVB in the PV industry again. With this, I conclude. I thank you all for your attention. I thank the Swiss Federal Office of Energy for partial funding and all the colleagues and all the experts in PV reliability that helped us performing this work and interpreting the results. Thank you very much to all of you. And if you need to contact us for more details, you can write to these addresses. And again, we have you have the references of our articles in the slide. Thank you so much.